Well, hello there, good people. Today, I have a little demo to show you. This is my thermometer. It's been sitting in the room for a while, so right now it says room temperature. Now, you probably can't see this because it's probably not in focus, but if you could see it, you would see it at 22 degrees Celsius, which is about the temperature in the room right now. That's a good, nice room temperature. Now, here I have a bottle of rubbing alcohol. This rubbing alcohol has also been sitting in the room for quite some time, and so its temperature is also room temperature. If I take this thermometer and I put it into the bottle here, then you'll see that the temperature is still room temperature. But now if I take this guy out like this and I wave it around like a magic wand, except that nobody would wave a magic wand like this, but if I wave it around like this, then you would see that the temperature on here is now much lower than room temperature, and you probably once again cannot see that now it says that we're at about 14 degrees Celsius. What happened? Did my room get colder? When I waved this thing around, is that what happened? Did the temperature in here all of a sudden drop to 14 degrees Celsius? Did you see me shiver as I said, oh, I need a little bit of a coat, it just got chilly in here? No, that's not what happened. What happened has everything to do with latent heat and states of matter. And those are our topics of the day. Today, we are talking about latent heat and states of matter. We'll actually talk states of matter first, and then after we talk states of matter, we'll talk about latent heat. Let's start by talking about states of matter. You know that there are maybe four states of matter, and they are as follows. We got solids. We got liquids. We've got gases. And we have plasma. Now, I like to ask students, which one is actually most stuff? Like in the observable universe, in the visible universe at least, what is most stuff made of? And the correct answer? Plasma. About 98% of the visible universe is made of plasma. But a lot of students don't really actually know what plasma is. They know what solids are, they know what liquids are, they know what gases are, blah, 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 blah. We know all of that. But they don't know what plasma is. Here's what they know. They know, well, in solids, you've got these molecules that are sitting and vibrating in kind of fixed positions. Then in liquids, those molecules spread out a little bit and they kind of tend to slide past each other. In gases, those molecules are super spread out and they're going all over the place. But what happens in a plasma? Well, you know that to go from a solid to a liquid to a gas, you have to add energy every time. What happens when you add energy to a gas? Well, if you add energy to a gas, you're not gonna make the molecules spread out. They're already very spread out. What's gonna happen is if you add energy to a gas, you're going to strip the electrons off. You add a little bit of energy in, and when you add that energy, the little electrons say, I can't hold on for much longer, and the electrons go flying off. And so the electrons leave the gas, and the gas becomes ionized. Plasma is just an ionized gas. It's just a gas without electrons. You've seen plasma before, most likely the last time when you went camping, because if you lit a little campfire, what is fire? Have you ever looked at fire and said, what is that? It's not a solid, it's not a liquid, it's not a gas, or is it? No, it's a plasma. Fire is just an ionized gas, and that's what things like stars are made out of, is plasma, which is why most of the observable universe is actually made of plasma. Now, you know a few other things about solids, liquids, and gases. You know that solids have a nice definite shape and a definite volume. Liquids have a definite volume, but they can have an indefinite shape. Gases have an indefinite shape and an indefinite volume. They can take up different amounts of space, and they can have any shape. They can fill the shape of their container. So you know those about these three things. Here's what else you know. I need some colors here. Okay, here's what else you know. You know that if we want to go from a solid to a liquid, we call going from a solid to a liquid melting. We also will call it, in this class, we'll call it fusion as well. If we want to go from a liquid to a gas, going from a liquid to a gas, our main word, the most generic word for that is vaporization. And then there are actually two different types of things that can be considered vaporization. The first thing is evaporation. And the second thing is boiling. When you boil something, you are changing, oh, there's the bell. When you boil something, you are changing the whole liquid from a liquid state into a gas state. The whole thing is getting transformed. You have to add a whole lot of heat to make all of that stuff go from a liquid to a gas. But in evaporation, it's just the little molecules up on the top, on the surface of the liquid. Those little molecules up on the top of the surface of the liquid, one of them gets a little bit of energy and it boop, breaks free from the rest of its friend. And then another one gets a little bit of energy, boop, it breaks free from the rest of its friends. And when they break free from the rest of friends, well, now they're all spread out, and so now they're a gas. Evaporation happens just on the surface of a liquid. Boiling happens in the whole liquid. And so that's the difference between these two. You also know that you could skip steps. You could go straight from a solid to a gas, and we call that process, you know, sublimation. This is the classic dry ice demonstration is, look, it's a solid, it becomes a gas, just like that. We call that sublimation. Now, we could also go back down the other way. If we go back down the other way, and we go from a gas to a liquid, you know, we call that condensation. If we go from a liquid to a solid, you know, going from a liquid to a solid, we call that freezing, or in this class, we'll also call it crystallization. Or you can skip steps and you can go from a gas straight down to a solid, and we call that either one of two words, deposition, or, now this is a real term, folks, you can also call it reverse sublimation. And I hope I'm like not too far away on my camera here and you can still see this here. We can call it deposition or reverse sublimation when you go from a gas straight into a solid. That's deposition or reverse sublimation. Now, I've drawn all of these processes in two different colors because these different types of processes can be categorized into really two categories. We call the ones that are in red here, these are endothermic processes, meaning that they require the addition of heat. The ones in blue are what we call exothermic processes because they release heat. Your endothermic processes require heat, your exothermic processes release heat. You know that this is true because just intuitively, you know that if you need to go from a solid to a liquid, like if you want to go from ice to water, you got to put heat into that ice to turn it into water. You know that if you want to go backwards, if you want to take water and you want to turn it into ice, you got to take some of the heat out of that water to turn it into the ice. So these things are exothermic. They release heat. You have to take heat out of the system in order to make these processes happen. These things are endothermic. You have to put heat into the system in order to make these things happen. Now, I knew about exothermic and endothermic processes when I was in 3rd grade. Because when I was in 3rd grade, one day we had outdoor recess. But it was one of those days where it was like, are we going to have outdoor recess? Are we going to have indoor recess? We couldn't really tell. But the adults and the citizens who ran that whole elementary school society, they decided that we were going to have outdoor recess. So we went outside for outdoor recess. And man, let me tell you, it was a very, very chilly day. Very cold day. And I remember starting out at outdoor recess and saying, whoo, it is cold. But then, as we were at outdoor recess, about halfway through, it got warmer. And I could feel that it got warmer. And all of a sudden, right about when it got warmer, these big, fat snowflakes started to fall from the sky. Now, this was confusing to me as a 3rd grader because as a 3rd grader, I knew something about snow. And I knew that snow is cold. And so this made no sense to me because I could feel that it actually got warmer. The air really did get warmer. But I thought, how could the air get warmer if now we have more cold stuff in the air? Because snowflakes are cold. And I got a bunch of big fat ones falling down in front of me. This was very confusing to me until I learned about endothermic and exothermic processes. Because if you got little raindrops in the sky, and those little raindrops in the sky have to turn into snowflakes, well, that's an exothermic process, the process of crystallization. It releases heat. You got to take a little bit of the heat from the raindrop out of the raindrop to turn it into a snowflake. Where does that heat go? Into the air. And so it was a warmer day on the days when the snow falls. The next time that it's forecasted for a snow, go outside and check it. Feel it right before it snows, and then go outside as it's snowing, especially if you have those big fat flakes, and you'll feel, wow, it's just slightly warmer when it snows. Isn't that nice? That's the same thing that happens here with my thermometer and my rubbing alcohol. I put it in. When I shake it, it evaporates. If the rubbing alcohol is evaporating, well, that's an endothermic process. It's got to get that energy from somewhere. Where is it going to get it from? It's going to steal a little bit from the thermometer and from the surrounding air. And so because it steals a little bit of heat from the thermometer says, whoo, I'm chilly. The same way that you say you're chilly if you get out of the pool. You get out of the pool on a summer day, you were really hot before you got in the pool, you get out of the pool and you're a little bit cooler. Why? Because now there's water on your skin. That water on your skin is evaporating. When it evaporates, it takes some of the heat from you with it. It's a nice endothermic process. Hey, do you notice how when we talk about endothermic and exothermic here, we have to be very clear because we're talking about endothermic and exothermic for the thing that is changing states. But if you change your perspective, water on your skin when you get out of the pool, that's an endothermic process for the water as it gains heat. But that's an exothermic process for you as you give up heat to the water. So here, when we say endothermic and exothermic, we're referring to the things that are actually changing states. But the things that are giving heat or taking heat from the things that are changing states, those will experience the exact opposite process in being consistent with the law of conservation of energy. Now, the next thing that we have to address is this concept of what we call latent heat. Latent heat, I'll give you a definition for it. Latent heat is the energy needed to go from one state of matter to the next for a particular substance. Latent heat is the amount of energy that it takes to go from one state of matter to the next for a particular substance. Pause the video if you need to and get that written down. We represent latent heat with the capital letter L. Hey, isn't that logical? Very nice, just as it always is. Latent heat is represented with a nice capital letter L. It's the amount of heat that it takes to go from one state of matter to the next. Now, not all substances take the same amount of heat or the same amount of energy to go from one state to the next. Some different substances will change their state of matter very, very easily. Other substances, it's going to be very hard for them to change their state of matter. We'll take a look at that in a second. For now, you know that when you add heat to something, that heat can do different things. And what we're going to talk about now, it's going to connect back to latent heat in a second. Sorry. Let me talk about what I'm doing. I'm going to pull away from latent heat for a second. We're going to talk about another category and then we'll pull latent heat back in to this new subject that we're going to talk about. So here's the new subject. Here's the new thing that I want to talk about. When you add heat to something, that heat could do multiple things. And this idea is going to be kind of like the foundation for everything, for the rest of everything that we're going to do in this lecture today. That heat that you add could do one of two things. Adding heat will either increase the temperature or change the state of matter. If adding the heat increases the temperature, it does that by speeding up molecules. Molecules. If adding heat changes the state, it does that by spreading out molecules. So adding heat will do one of two things. It will either speed up the molecules, make them move faster, increase their kinetic energy, give you a higher temperature, or it will spread out the molecules, going from a solid to a liquid or a liquid to a gas. It'll spread those molecules out. Now, here's the key. If you add heat, it will do one of these two things, but never both. Let's take a look at a graph. This is a classic graph that you've seen before in your childhood. On this axis, and by your childhood, I mean like last year and probably also in 8th grade physical science. On this axis, I'm going to put heat. And on this axis, I'm going to put the temperature in degrees Celsius. And now I am going to show you a graph of what happens to water as you add heat to it. Let's actually start with some ice here. So let's start down here at, I don't know, maybe like negative 20 degrees Celsius, something like that. Ice will start at negative 20 degrees Celsius. Here we have 0 degrees Celsius. Up here we'll have like 100 degrees Celsius. We can even, let's go all the way up to 110 degrees Celsius. Why not? Now here's what happens. If you have ice that starts at negative 20 degrees Celsius and you start to add heat, the first thing that heat will do is it will increase the temperature. It'll speed up the little vibrating molecules inside of that ice. And so it'll make them speed up and it'll increase their kinetic energy and the temperature will go up. That will happen until you get to 0 degrees Celsius. Once you get to 0 degrees Celsius, you know that 0 degrees Celsius here, this is what we call the melting point or the freezing point, depending on which way you're going, for water. When ice gets to 0 degrees Celsius, it melts. When water gets to 0 degrees Celsius, it freezes. So the ice will heat up, heat up, heat up, heat up until it gets to 0 degrees Celsius. At 0 degrees Celsius, now this ice isn't going to stay ice anymore. Now it's going to turn into water. When it turns into water, it's changing its state. All of the heat that you put in when it's at 0 degrees Celsius will go towards spreading out the molecules. The heat won't go towards increasing the temperature or speeding up the molecules because the heat is already being used to break all of those little ice molecules apart from each other and turn it into a liquid. So the temperature will stay the same because the energy is going to changing the state. So the temperature will coast right here at 0 degrees Celsius. When we start here at 0 degrees Celsius, we have 0 degrees Celsius ice. When we end here at 0 degrees Celsius, we have 0 degrees Celsius water. Then after that, the water then increases its temperature. If you continue to add heat, the water then increases its temperature. So the water gets hotter and hotter and hotter and hotter up until we get right here to 100 degrees Celsius. You know that 100 degrees Celsius is the boiling point or the condensation point. Condensation point, depending on which way you're going, for water. So when this water gets to 100 degrees Celsius, now adding heat isn't going to change the temperature anymore. Now it's going to spread out those little molecules and turn liquid water into water vapor, or what we call steam. So at that point, as you continue to add heat, the temperature is going to stay nice and constant as that water is becoming steam. Here we start with water at 100 degrees Celsius. Here we end with steam at 100 degrees Celsius. Then after that, if you continue to add heat, keep putting heat into the system, then the steam will increase its temperature. It's speeding up the molecules until it gets to 110 degrees Celsius. Now, let's go back through and let's model what happens in each of these phases. Here in this first phase, you have, right there, you have ice that is warming up. Ice warming up. Here in this next phase, staying constant at 0 degrees Celsius, you have ice that is becoming water. Then in this next phase, the water is getting warmer and warmer and warmer. So this is water warming up. Then at this next phase, you have water becoming steam. And finally, at this last phase, you have steam warming up. Do you see how every single time the heat is either used to increase the temperature or to change the state, but never both? So in places where the state is changing, the temperature is constant. In places where the temperature is changing, the state is constant. And there's a little graph. We know that we can use a formula that we know to calculate how much heat it takes to change the temperature. And that formula that we know is mc delta T. Well, we also have a formula for how much heat it takes to change the state. And this is where latent heat comes in. The amount of heat that it The amount of heat that it takes to change the state is equal to the amount of stuff that you have times the latent heat of that stuff. If that stuff has a greater latent heat, then it will be harder to change the temperature of. And if there's more of it, I said change the temperature. That's very, very bad. I mean change the state. Oh gosh, please rewrite anytime that I just said when I was referring to this. Please rewrite anytime when I said change the temperature because I was supposed to be saying change the state. Okay, it depends on the amount of stuff that you have. If you have more stuff that you need to change the state of, it's going to require more heat. If it's harder to change the state of that stuff, then it's going to require more heat. please add this equation to your bag of tricks and then open up to page 318 of your textbook. Let me go ahead and grab my textbook really quick. One moment. Oh, there's the bell. Okay. Here is my textbook. Wait, are we recording? One second. Okay, yes, fine. Okay, and we're back. Okay. So if you look at your textbook here, at the bottom of page 318, you can see that it says Table 6, latent heats of fusion and vaporization at standard pressure. Whoa, latent heats of fusion and vaporization, what does that mean? Well, that means that there are two different types, actually there are truly three different types of latent heats. We have latent heat of fusion, latent heat of vaporization, and latent heat of sublimation. Latent heat of fusion is the amount of energy or the amount of heat that you have to put in to go from a solid to a liquid. Latent heat of vaporization is the amount of heat or the amount of energy that you have to put in to go from a liquid to a gas. Latent heat of sublimation would be the amount of heat that you have to put in to go from a solid to a gas, although that's not one that we're going to talk about as much. We're mostly going to talk about latent heat of fusion and latent heat of vaporization. Now, latent heat of fusion is the amount of energy that you have to put in to go from a solid to a liquid. And latent heat of vaporization is the amount of energy that you have to put in to go from a liquid to a gas. But you could also go the other way. How much energy do you have to take out to go from a gas to a liquid? Or how much energy do you have to take out to go from a liquid to a solid? The amount of energy that you have to take out to go from a liquid to a solid, we call that the latent heat of crystallization. Excuse my tiny handwriting there as I try not to run into other things. Then, if I want to talk about how much heat do I have to take out to go from a gas to a liquid, we call that the latent heat of condensation, like this. Now, here's what's true. The amount of heat that you have to put in to melt something to go from a solid to a liquid is the same as the amount of heat that you have to take out to go from a liquid to a solid. And the amount of heat that you have to put in to go from a liquid to a gas is the same amount of heat that you would have to take out to go from a gas to a liquid. So these guys are the same, except that for crystallization, you're taking that heat out, which we indicate with a negative sign, and for condensation, you're also taking that heat out, which we indicate with a negative sign. This is why your textbook, if you look, it only includes values for the latent heat of fusion and the latent heat of vaporization. The reason why is because if you know the latent heat of fusion, you know the latent heat of crystallization. If you know the latent heat of vaporization, you know the latent heat of condensation. They're just the same thing except with a little negative sign there. Now, those are our types of latent heat. So what you would do is if you wanted to use this equation, you'd plug in the mass and then you'd plug in the particular type of latent heat. Notice that some substances are easier to change the state of than others. If you look at this table, you'll see that aluminum has the highest heat of vaporization, which means aluminum takes the most energy to vaporize. Meanwhile, nitrogen has the lowest latent heat of vaporization, which means nitrogen is the easiest on this table to vaporize. That also means, by the way, that it's the easiest to condense. And aluminum would be the hardest to condense. You'd have to take out the most amount of energy in order to condense it. Okay, that's a little bit on latent heat. What we're going to do next is we are going to try a little bit of a practice problem. This practice problem is going to come from this calorimetry worksheet here. We have questions number 6, 7, 8, 9, and 10 that you have assigned for you. We are going to start by looking at question number 9, and then after that we're going to take a look at question number 6. Let's go ahead and start by taking a look at question number 9. We are not going to do this whole problem together, but I am going to get it started for you so then you can finish it out on your own. Give me a quick second because I'm going to erase the whiteboard, so I'll pause the video, get the whiteboard erased and ready to go, and then we'll look at question number 9 together. One moment. Okay, we're going to be starting by looking at question number 9 off the worksheet. Here's what question number 9 says. Okay, question number 9 says, how much heat is required to convert 100 grams of ice at -20 degrees Celsius into steam at 110 degrees Celsius? To start this problem, we're going to always start any of these kinds of heat transfer problems where you have phase changes. We're going to start by drawing a little graph of the situation. On this axis, I'll have my temperature in degrees Celsius. On this axis, I'll have my heat in joules, the amount of heat that I add. In this case, I start at negative 20 degrees Celsius, so I'm going to include the negative 20 degrees Celsius here. Then on this line here, I'm going to put 0 degrees Celsius. I'm thinking 100 degrees Celsius is probably going to be pretty significant, and I end at 110 degrees Celsius. And so those are the axes that I draw. After I draw those axes, then I'm thinking, okay, I need to show ice that is becoming steam, so I'm going to draw that. I start with ice at negative 20 degrees Celsius. If I add heat, that temperature is going to increase until we get up to 0 degrees Celsius. Then that ice is going to turn to water. Then that water is going to increase in temperature until we get to 100 degrees Celsius. Then that water is going to turn to steam. Then that steam is going to increase in temperature until we get to 110 degrees Celsius. Now the next thing that I do is I'm going to label my initial and my final states here. When I label my initials and my finals, on this one it's pretty simple, not really all that complex, but on other ones it will get way more complicated, especially when we have two things going on at once, which we'll see in the next problem. But so what I'll do is I'll say, hey, this is my end, or my T final. This is my start. Here's my T initial at my start. And I'm gonna go from start to finish here. Now the question is, what is the total amount of heat that is transferred to the ice in order to get it to be steam? Now, when I'm looking at the total amount of heat, I'm thinking, wow, this ice is really gonna have to go on a journey. First, the ice is going to have to heat up. We'll call that part A. Then the ice is gonna have to turn into water. We'll call that part, whoa, not A again. We'll call that part B. Then the water is going to have to get warmer and warmer and warmer and warmer. We'll call that part C. Then the water is going to have to turn into steam. We'll call that part D. Then the steam is going to have to heat up. We'll call that part E. Wow, that is quite a journey. We got 5 parts. If you want to know the total amount of heat that this whole process is going to take, it's going to take the amount of heat for part A plus the amount of heat for part B plus the amount of heat for part C plus the amount of heat for part D plus the amount of heat for part E. Now, what I'm going to do next is I'm going to go through each of these parts individually, and I'm going to identify how much heat is actually transferred in that process. Now, I have 2 equations that I have that can help me in this situation. Sorry, I need some colors. We know that Q is equal to MC delta T, and we also know that Q is equal to ML. We use Q equals MC delta T on all the places where we have a temperature change. That's all the slanty parts. So part A, part E, and part C. Don't ask why I went in that order. We are going to use Q equals ML for all the places where we have a phase change. So that's part B and part D. So here's what I'm looking at. I'm going to change all of these Q's into either Q equals MC delta T or Q equals ML. I'm going to start with, for part A, Q equals MC delta T. So I'm going to plug in the mass of, check it out, it's the mass of the ice that I start with, times the specific, so I'll do mass of, actually, well, so here's what's going to happen. I'm going to come back to my subscripts here on my mass, because I'll explain it in a second. So I'm going to change this to an MC delta T. I got MC delta T. My subscript here for this C, this is the specific heat capacity of ice. Because it's ice that's going to be changing temperature. Notice the specific heat capacity of ice is not the same thing as the specific heat capacity of water. It's not the same thing as the specific heat capacity of steam. They all have different specific heat capacities. You can see that on page 314 of your textbook, taking a look at table 4. This change in temperature here, this change in temperature isn't going to be the change in temperature for the whole journey. No, it's just going to be the change in temperature for part A. So that's going to be the change in temperature of the ice. It's going to be from 0 degrees Celsius is my final, and negative 20 degrees Celsius is my initial. Then I add in the change in heat from part B. My change in heat from part B is the mass that I have from part B times L, the latent heat of, let's check. At this point, we know that there are 3 different types, there are 4 really types of latent heats that we're really going to be looking at. The latent heat of fusion is what we're going to use here, because this is something that is melting, and so because it's melting, we're going to use latent heat of fusion. Then for part C, I take a look. Here I have water that is heating up. For water that is heating up, I'm going to use MC delta T. Now I have to be careful. My C here is going to be the specific heat capacity for what's happening in section C, which is water. So this is going to be the specific heat capacity of liquid water. My delta T here is going to be my change in temperature for the water. That means my final temperature is going to be 100 degrees Celsius and my initial temperature is going to be 0 degrees Celsius for part C. Now I look at part D. For part D, now I have water going into steam. I'm going to use ML because this is a phase change, so I got M. L here. In this process, this is getting vaporized. It's going from liquid to a gas, so I'm going to use the latent heat of vaporization. Then for part E, I got a change in temperature, so I got an MC delta T. For this, I have, for my C, this is steam that's getting warmer. So my specific heat capacity is going to be the specific heat capacity of steam. My change in temperature here is going to be the change in temperature of steam. It's not my final minus initial overall. It's my final for the steam section minus my initial for the steam section, 110 minus 100. Now that I've done this, you'll notice that I didn't put subscripts on the M. That's because the M is the same here for everybody. The same amount of mass that I had to start with is the same amount of mass that I have to end with. So a few little algebra things here. First, if you want to pull this M to the outside, then you can pull this M to the outside of this algebraic statement, and that'll clean things up a little bit. So then I have specific heat capacity of ice times the change in temperature of ice, plus the latent heat of fusion, plus the specific heat capacity of water, plus times the change in temperature of the water, plus the latent heat of vaporization, plus the specific heat capacity of steam, times the change in temperature of the steam. Now, the last thing that I'll do here, before I can plug in any numbers, is I gotta split all those deltas into finals minus initials, because I wasn't given deltas, I was given finals and initials here looking at this diagram. So I pull my mass out here, I have my specific heat capacity of ice, I'm gonna change this into the final temperature of ice minus the initial temperature for the ice. This, when I'm looking at it here, I'm paying very good attention to my graph. This is where your graph is going to be your guide for the whole rest of your problem as you're pulling numbers. Plus the latent heat of fusion. I'm gonna make these actually like boxy parentheses. Yes, perfect. Plus the specific heat capacity of water. Change in temperature for the water is the final temperature of the water, of the liquid water, minus the initial temperature of the water. Here, when I look at my diagram, I'm gonna say my final is 100 and my initial is 0. Then I got my latent heat of vaporization. Then I got the specific heat capacity of steam times the change in temperature for my steam. The change in temperature for my steam is going to be the final temperature of the steam. That's going to be 110 degrees Celsius minus the initial temperature of the steam. And there's our equation. Now we can plug in numbers. Let's talk about the numbers that we're going to plug in. We were given, I didn't write down my knowns and unknowns. Oh my GOSH, that is embarrassing. It told me that the initial mass of the ice was 100 grams. 100 grams feels okay to me, but 0.100 kilograms, that feels even more awesome. It starts, we have our initial temperature here, and our final temperature is right here. So, hi Hamdia. Pretty good, how are you?
Good.
So this is my final temperature here, this is my initial temperature here, and I was given my mass, but these finals and these initials, careful, they're not the same as these finals and initials. So what you do is you have to look at your graph and you have to make sure to pay very, very close attention to what is happening in each of these different sections. Then you can plug in numbers, and when you plug in numbers, you should get to a final answer if you did this correctly of 5.1, oh no, I can't tell if I wrote a 3 or a 5. I'm gonna go 3.1 times 10 to the 5th joules. Something along those lines. That is a total heat problem. I call it a total heat problem because you're looking for the total heat for a whole thermal process. What we're going to do next is we're going to do a little bit of a calorimetry problem, and we're gonna look at question number 6. I'm gonna go ahead and clear my whiteboard here. For question number 6, same as question number 9, you are going to draw a graph every single time, and you'll see that in this one, it's so very helpful to have that graph as a nice little picture to assist you, especially in this one that gets a little bit more complicated. Let's take a look at question number 6 together. Here's what question number 6 says. It says, steam at 100 degrees Celsius is condensed in 200 grams of water at 25 degrees Celsius. How much steam will be required to raise the temperature of the water in the cup to 50 degrees Celsius? Okay, let's talk about the setup of this problem. You got a few options for how you heat up a pot of water. What you could do is you could take a pot of water, you could put it on the stove, and you could heat up the water that way. Or here's another option, a more creative option. You could take a bag of steam. You could put that bag of steam in the water. If you put the bag of steam in the water, well then the heat will leave the steam and enter the water as the steam cools down. That is the very creative situation that we have here. This is a combination of a phase change problem and a calorimetry problem, because the amount of heat that leaves the steam is going to be the amount of heat that is gained by the water. Let's go ahead and start by drawing a picture. Here's what we do first. I draw my classic little graph here. I'm gonna start at negative 20 degrees Celsius again. Here I got 0 degrees Celsius. Oh gosh, I should probably label. This is my temperature in degrees Celsius. This is the amount of heat that I put in joules. Again, this is just a nice rough sketch. 100 degrees Celsius, we'll go up to 120 degrees Celsius, because why not? We start with ice. Down here has to heat up, then it becomes water, then the water heats up, then the water becomes steam, then the steam heats up, and that's our little graph. Now what we're going to do, same thing as last time, is we're going to label our initial and final. Now, here's what's going to happen. Sorry, I'm kind of trying to choose two colors here. I'm gonna go orange and red. Okay, that feels crazy, but I think it's gonna be fun. Okay, yeah, I guess I'm doing it. Whoa, I'm throwing markers everywhere. Okay, we got orange and red. So here's what happens. I have two things that are happening at once. First, you have steam that's cooling down, and you also have water that's heating up, and those two things are happening simultaneously. So I'm gonna draw those two things that are happening on my graph. We're gonna start with the steam cooling down. It says that the steam is at 100 degrees Celsius to start. So I'm gonna start with steam at 100 degrees Celsius. Here's my initial temperature, in particular for my steam. Then my steam is going to, when it gets put into the water, it's going to cool down. Let's see what happens to my water. My water starts at 25 degrees Celsius. So I'm gonna draw over here. Here's at about, well, this is not really right. Gosh, I'm gonna say that's 25. Thanks for coming to my rough sketch. Okay, here's that, okay. So let's say that this is about 25 degrees Celsius. The water starts at 25 degrees Celsius, and the water ends, our goal is to get that water up to a final temperature of 50 degrees Celsius. So this is gonna be my initial temperature of the water, and this is going to be my final temperature of the water. Well, that steam is also going to cool down until that steam has the same temperature of the water. So the steam is going to cool down until this is also the final temperature of the steam. Let's check the journey of each. The water starts as 25 degrees Celsius water and ends at 50 degrees Celsius water. The steam starts as 100 degrees Celsius steam, cools down to become water, and ends in thermal equilibrium with the water at this final temperature. Okay, the question is, how much steam do I need in order to get that water up to that final temperature? We're going to start with a calorimetry statement. Here's what we're going to say. The amount of heat that's lost by the steam. Notice I do a negative sign to indicate that that is the amount of heat lost. The amount of heat lost by the steam is going to be the same as the amount of heat gained by the water. When I look at the journey of the steam has two parts to it. Notice, first, the steam has to turn into water, and then that water that used to be steam has to cool down. We'll call this part A and part B. So when I'm looking at the change in temperature of the steam, I am going to start here with, change in temperature. I meant the heat lost by the steam. I have QA and QB are both together making up the total heat that was lost by the steam. Now let's look at the journey of the water. The journey of the water, oh, sorry, I should include better subscripts. I should still say steam and steam. Okay, good. Now let's look at the journey of the water. The journey of the water is very simple. It's just water heating up. So I only really have one change in temperature for the water. I only have a part A, there's no part B, there's nothing funky about that. Now, the next thing that I'm going to do is the same thing that I did in the last problem. I'm going to replace all of my Q's with MC delta T's and with ML's as appropriate. First, let's start on the steam side. When I look on the steam side, I say, okay, first I have part A. In part A, that's a nice flat line. That steam has to become water. In order for the steam to become water, I'm going to need a negative mass of steam times the latent heat of, oh, quick check here. This is interesting. This is going to be the latent heat of fusion, or the latent heat of vaporization, or the latent heat of crystallization, or the latent heat of condensation. Which one's happening here? The steam is condensing. So this is going to be my latent heat of condensation for the steam. Then, after that, I have QB. For QB, that's going to be the change in temperature of the steam. The change in temperature of the steam is going to be this little section here. That's going to be the mass of the steam times C delta T, MC delta T. That change in temperature is going to be from right here down to right here. So I'm going to put B because it's the change in temperature for region B. And now let's check this guy here. Do you see that after the steam has gotten to this point here, do you see that now that steam isn't steam anymore? Now that steam is water that is cooling down. So for my specific heat capacity, I'm not going to do the specific heat capacity of steam. I'm going to do the specific heat capacity of water, because now it's water cooling down. There's that side. On the other side of the equation, the much simpler side of the equation, really, I have the change in heat of the water. The water is just changing its temperature, so its change in heat is just going to be an MC delta T. Did you notice that I used good subscripts on the mass here? Well, that's because this mass is different than this mass, because we got two different things that are happening here. The mass of this is the mass of the water. Now I check my chart. This water is heating up. It's always water, so it's going to be the specific heat capacity of water times the change in temperature of the water specifically. Okay, that's our start. Now, the next thing that we're going to do is that we have a few things to attend to in terms of our positive signs and negative signs. Here, my latent heat of condensation, I actually am not given a value for the latent heat of condensation, but here's what I do know. Sorry, trying to decide where to put this. I do know that the latent heat of vaporization is negative the latent heat of condensation. And I know that the latent heat, that means that the latent heat of condensation is negative the latent heat of vaporization. So I can plug in here for this latent heat of condensation, I can plug in negative the latent heat of vaporization. Then, next I'm going to add in the mass of the steam times the specific heat capacity, once again, of water, times the change in temperature for part B. Oh, I was going to change it. Okay, wait, yeah, let's do that too. So there's the first trick. The first trick is that you have to sub in for the latent heat of condensation. You have to sub in negative the latent heat of vaporization. Now we got to change these into finals minus initials. I'm going to do this as the T final for section B on my graph minus T initial for section B on my graph. Notice that T final is going to be the same for both the steam and the water. Then I set this equal to the other side, which says that we have the mass of the water times the specific heat capacity of water. Oh geez, I'm running out of space. This is so embarrassing. Times the final temperature of the water. Minus the initial temperature of the water. Whew, that is very tight. Now, I have done all of my kind of sign work here. I've changed all my delta T's into finals minus initials, but I'm not done yet because now I actually have to solve for what I'm looking for. What I'm looking for is the mass of the steam that is needed in order to get this job done. So what I'm going to do next is I'm going to factor out the mass of the steam. Sorry, I'm going to change out this red for a different red. A red that's still strong and youthful. Okay, so I pull out the mass of the steam out of this side of the equation, and I'm left with, actually, we'll leave our negative sign out here. I'm left with negative latent heat of vaporization plus the specific heat capacity of water times T final for part B minus T initial for part B. And that is going to equal the mass of the water times the specific heat capacity of water times the final temperature of the water minus the initial temperature of the water. Like this. Now, my next step is a little bit of algebraic rearranging. What I'm going to do is I'm going to divide both sides by what I have going on here. When I divide both sides by that statement, I get that the mass of the steam, and I'm also going to divide both sides by that little negative sign there. The mass of the steam is equal to the mass of the water times the specific heat capacity of the water times the change in temperature of the water from final minus initial. All of that is going to be then divided by, I got a negative sign out front, negative latent heat of vaporization plus the specific heat capacity of water times the final temperature from part B minus the initial temperature from part B. And now I'm ready to plug in numbers. And that is really pretty much it. There are a few sneaky things here. Again, you have to change this latent heat of condensation into a negative LV. You have to pay attention because this specific heat capacity is not the specific heat capacity of steam, because now that steam has become water, so that C is going to be the specific heat capacity of water. And then also you have to pay attention to which temperatures you're really plugging into this equation here. But from there, you could kind of plug in numbers and get to a final answer. And if you do it right, let's see. The mass of the water that was given to us, let's see, was 200 grams of water. Oh gosh, I didn't write down my notes and notes, but you could do that. 200 grams of water. That's 0.200 kilograms of water times the specific heat capacity of water. I know the specific heat capacity of water is 4.186 times 10 to the third joules per kilogram degree Celsius. That's a bad J. That's a backwards J. Wait, no, that was a forwards J. And then I turned it into a backwards J because I got crazy. Then the final temperature of water here is going to be that 50 degrees Celsius minus the initial temperature was that 25 degrees Celsius. Take that and divide it by, and this is where you are most certainly going to need your textbook. You're going to need your textbook to find a few constants. What I'm going to do is I'm going to open my textbook up to page 318. I like to keep a little sticky note on that page. It's super helpful to me when I'm looking up these latent heats. I look up, okay, what is going to be my latent heat of, oh gosh, wait, no, I don't have it. Where is my latent heat of vaporization for steam? Oh, well, this is really embarrassing, actually. Oh, it's for water. Water. Okay. I do have it. I almost just got really very stressed there. Okay. My latent heat of vaporization for water, I look on this table and the latent heat of vaporization is 2.26 times 10 to the 6th. And don't forget your units here. We got joules per kilogram. Then, oh, not another parenthesis. Not that. Then I'm going to add in the specific heat capacity of water once again, which is 4.186 times 10 to the third joules per kilogram degree Celsius. Now I happen to have that one memorized, but if you got to one that you didn't know, like for example, the specific heat capacity of ice, and you did not have that memorized, you would have to flip to page 314 of your textbook, where you would look at the top of table 4, or the top of the page of table 4, where it would tell you that the specific heat capacity of ice is 2.09 times 10 to the third. But that's okay because we just need water and we know it deep down in our hearts. Then I multiply this by the final temperature for part B minus the initial temperature for part B. For the steam, it ends at, oh, whoa, sorry. It ends, wow, that could have been so dangerous. Could that have been so bad? It ends at 50 degrees Celsius. And it started at 100 degrees Celsius. Whoop. That is really crammed in on the end there. Plug this into your calculator, and I'm starting to feel like you can't even see this anymore. Plug this into your calculator, and you get the final answer that I do believe is you would need 0.0085 kilograms of steam to get the job done. And that is pretty much all for today, folks. We talked about states of matter. Then we talked about latent heat, and we talked about how you can do problems that have a total heat kind of problem. And then this kind of problem is a different kind of problem. I call this a calorimetry problem because it's a calorimetry problem in combination with the phase change problem. Do always, always, always draw a picture. That'll be incredibly helpful to you. Write down what heat is being lost, what heat is being gained. Make sure that then you split that down into its separate parts. Plug in, be very careful when you plug in your variables here, and then plug in algebraically rearrange, plug in numbers, and you're good to go. And that is pretty much all for today, folks. I hope you have a wonderful rest of your day. I do have to walk all the way around the table before I can end the video, so it's probably going to end awkwardly with me saying, have a wonderful rest of your day, and then a few seconds of silence as I walk around. Okay, bye guys, have a wonderful rest of your day.